Hello everyone, we're back with Math 2413, Calculus 1, in our last section of Chapter 4, which is primarily about undoing chain rule, either through pattern recognition, which I don't recommend, though as you get more experienced you can use that. More likely that you're going to be using substitution until you are more familiar with how the process works. So again, you have two options. But I'm always going to show you using U substitution, so that's kind of the method that we're going to talk about. Now we know from the chain rule, when you take the derivative of a function with another function inside of it, you have the derivative of the outside function with the inside unchanged, and then it's multiplied by the derivative of the inside function. That also means, though, if you have that set up, this derivative set up and you're integrating, it should go back to the original. Now, how are you going to recognize that? Usually something complicated will be happening to one kind of function, and its derivative should be sitting on the outside of whatever complicating that's happening, allowing you to substitute. And the way we do this sometimes is we let u equal whatever the complicated looking thing is, and then unlike, say, u substitution in college algebra or any other time you've seen it, this requires you to also deal with the dx and convert it to du so that you can take the integral with respect to u. Now, this is a lot of talking at you, but the easiest thing to do is to show you how this works. So we've got, for example, integrate the integral of x squared plus 1 squared times 2x dx by letting u equal x squared plus 1. So if we let u equal x squared plus 1, if I want to convert everything to u, I need my variable of integration to be u, which means I need the derivative of u, which is du, take the derivative of the left, is equal to the derivative on the right, 2x dx. And what I'll notice is the 2x dx is sitting in the problem, as is my original u, x squared plus 1. So if I convert both of those pieces, this x squared plus 1 now becomes u. It's still squared, but 2x dx becomes my du, and all of a sudden I have a very basic power rule integration that wasn't necessarily apparent before. Now what's the integral of u squared with respect to u? It would be 1/3 u cubed plus c, or u cubed over 3 plus c. Now, because the problem didn't start in terms of u, I shouldn't end it in terms of u either. The whole point of this was to make the integration easier. But what is u really? It's x squared plus 1. So this is really 1/3 times x squared plus 1 to the third power plus c. Now, one thing, as we talked about before, that you can always do when you're integrating is you can always take the derivative of your answer and see if it gets you back to the original, which in this case it would, because the 3 would come down, cancel out the 1/3. We would have x squared plus 1 squared, but using the chain rule, we would then multiply by the derivative of the inside, which would be our 2x, and of course the c would go away when we take the derivative. Now, not all the time are you going to have exactly what you need on the outside. Sometimes you have pieces of it. For example, if you have x times x squared plus 1 squared dx, I know the derivative of x squared is 2x, so one thing that I can do is say, hey, u equals x squared plus 1, and I know from above du equals 2x dx. But right now, besides the x squared plus 1 squared, I only have an x dx, so I can divide by 2 and say, well, if I've only got an x dx, I can just substitute in du over 2. The other option that we would have had is to put a 2 on the inside and a 1/2 on the outside, so basically multiply by 1/2 and multiply by 2. It would produce the same result. What that means now is my integral becomes now u squared like it was before, but now it's times du over 2, or 1/2 du, but I can move the 1/2 outside the integral, and then integrate that same u squared that I got before, so now it's 1/2 times the 1/3 u cubed plus c. And if I distribute it through, this is now 1/6 u cubed, 1/2 times a constant is just another constant. Since it was arbitrary, we don't need to worry about distributing it there. 1/6 u cubed, what was u really? X squared plus 1. So this is 1/6 times x squared plus 1 cubed plus c. Now we kind of expect it. Our integral is half the size it was before, so we're expecting the answer to be half the size that it was as well. But this change of variables mainly is to help illustrate that we don't necessarily need the exact derivative sitting there to use the pattern. Multiples of the derivative are just good enough for us to deal with. Similarly, integrate the integral of the square root of 2x minus 1 dx. Remember, this is the integral of 2x minus 1 to the 1/2. But again, what's something inside, the complicated thing would be the square root happening to the inside. We kind of want to see what happens if u is 2x minus 1. Then again, we have to accommodate for du. It's 2 dx. I don't have a 2, but I have a dx. So that means du over 2 is equal to dx. And now I can use my substitution. U is the 2x minus 1, so this is u to the 1/2 times du over 2. And again, we can bring the 1/2 out front. And now I have a u to the 1/2 du, and I can integrate that. We go up to our new power, u to the 3/2. This is 1/2 times u to the 3/2 divided by 3/2 plus c. I'm careful here, 1/2 divided by 3/2, or 1/2 times 2/3, is 1/3 u to the 3/2 plus c. And again, did we start with u? No, we did not, so I have to put back what it is, 1/3 times 2x minus 1 to the 3/2 plus c. So this is generally how we can clean up some complicated products that look like there's a relationship between what's inside a function and what's outside in terms of their relative power. So what are our general guidelines? We would like to choose a substitution that is generally inside the composite function. So if there's multiple complicated things going on, think as far inside as possible. Try to find what that thing's derivative is and see if there's an easy substitution to be made. You rewrite the integral in terms of u, you integrate and get an answer in terms of u, and then you replace your whatever u is equal to in terms of x. The most common u substitution is similar kind of to what we see there, is like the power rule, applying the power rule after substituting. So there's more practice down here. I'll do a few of them and then we'll continue in the next video. There's some more complicated ones on the next page. Now again, if you let u equal 3x minus 1, then du equals 3 dx. This integral, here's our du, becomes u to the 4th du. The integral of that is u to the 5th over 5 plus c. But what was u really? It's 3x minus 1 to the 5th over 5 plus c. And I'll do b and I'll leave c for you to try. So again, the more it's not clear which one of these is the more complicated. It's true we could multiply these two out and then integrate with a bunch of power rule. But I also might be able to notice that if u is x squared plus x, then du is 2x plus 1 dx. So that this becomes my du, and this becomes the integral of u du. And the integral of that is u squared over 2 plus c. But what was u originally? X squared plus x squared over 2 plus c. Like I said, I have some ones with trig functions that are more complicated on the next page, and then we'll talk about how this relates to definite integrals in the next video.